There we go.
Cool. Hi, everyone. My name is Tal. I'm a software engineer at Oodle. Today, I want to talk about the serverless Prometheus and walk you through our journey building serverless Prometheus and the challenges we faced in this journey. So here's the outline. So we'll briefly touch about on our architecture based on serverless and object store, and our journey, and the challenges we faced. Then we'll talk about the benefit from this architecture, and we'll do a quick demo. Our design goal is cost, query performance, and scalability. But in this session, I'm going to focus on the latency query performance. This is a high level architecture based on serverless and object store. The query engine invokes thousands of Lambda functions, 2 S3. Each Lambda function will only does at most 2 S3 gets. And each function only scans a small portion of the data in the file, thanks to the columnar data file format that we implement. I want to talk about our experience dealing with the large response payload. In our first iteration, we use the default buffer invocation for Lambda, which has a 6 MB payload limit. Our Lambda function error outs for any high cognitive metrics. So we went about to our second iteration, implementing the Lambda streaming, which is the newer offering from last year. The streaming has 20 MB payload limit, which is a soft limit. You can raise this limit. But the problem is the data transfer rate is still capped after 6 MB. We went to our third iteration, trying to reduce the payload, trying to maintain under 6 MB. So we did a string interning, by the way, so there's a great talk today for string interning and yesterday. And we decided to trade off the CPU for data size. So we are going to compress and decompress during the data transformation. Our current iteration, basically, we are going to put large payload on S3, and we achieve a 2x query performance. So this architecture provides a number of benefits. In cost, in storage, we don't have disk. Every data is processed in S3. Lambda is paid for what you used. Running Lambda in parallel helps us to achieve our P9 latency under 3 seconds. Our storage engine and compute can scale independently and indefinitely. So I want to run a quick demo. So what you see here is the playground, Oodle playground. Basically, the query is very simple, sum rate function, but the metric name is different. So I want to kind of choose a random one, so to make sure this is not cached. Let's say today's lucky number 22. Let's say 12 hours. So you can see the query comes back really quickly, and we can increase the number, this temperature as well. So I'm doing 2 days now. You can see this basically was trying to meet our design goals. We can do even 7 days. So I want to show you a little bit kind of stats under the hood. So what happened behind the scene? So this is a query from the CloudWatch. So it's not this is an old query, but because latency, I don't have time basically to wait for the CloudWatch to generate. So basically, you can see from here, each query will invoke thousands of Lambda functions, and quickly goes to 0 once the query is gone. What I want to show you again is the kind of real-time this latency I just filed, and then we can look at logs, see what's basically for one single Lambda function, what's the log looks like. So here, this is CloudWatch group, CloudWatch logs, and I'm querying this number because I know for each matrix is this is the number of time series in this matrix, and we can go into one log line. This shows the number series is this number, and the unpressed is very close to 6 megabytes, and that's why we basically have to do compress. So keep maintain the under 6 megabytes. So we can also just search in this string, see if we can find one single query. So we don't log a lot because we have maybe thousands of non-functions. So we're trying to do log minimum. From here, you can see each non-function they basically can finish in 1 second, on a second, 1 second. So in this case, it's 600. We allocating 4 gigabytes in memory, so which roughly give us 1 CPU. Okay, we're done. Okay. Thank you.